helicopter again. So first thing, the three forces, we know that this is lift, this is weight, and this is the drag. Okay, so we know those three forces. Now, once again, we know this helicopter is moving at a constant speed. And because of that, we know from GCSE that when any object is moving at a constant speed, the total resultant force on it must be 0. Okay, so we've got to bear that in mind. Now, I'm going to show you a different method how to do this. The way we're going to do this time is to split the lift force into vertical and horizontal components. Now, it looks like the lift force is acting here, but actually the three forces we're going to say are acting from this point here. So that means that the drag's acting that way, the weight that way, and then the lift this way, okay? And we can split the lift into a vertical component and a horizontal component. Okay, whoops, there's the horizontal component there. Now, although it doesn't look like it from the diagram because these arrows are two different lengths, the horizontal component of lift and the drag are in opposite directions and they must be equal in magnitude so that they cancel out. The weight and the vertical component of lift they're in opposite directions and they must be equal in magnitude so that they cancel out. And then that means that there's no resultant force on the helicopter. So let's work out the vertical component of lift. So if I draw the lift force over here, it'll be easier. So we're going to show the vertical component of lift there. Okay. Now, we can then show the horizontal component of lift there. That angle there is 74. So this angle here must be 16 because 74 plus 16 makes up the 90-degree angle between the vertical and the horizontal. Now we know that this is 9.5 kilonewtons. So we're going to work out, first of all, the vertical component of the lift. And the way we can do that is if we think of this as a triangle, so that actually there's your horizontal component of lift, your vertical component of lift, and then that's the resultant force. So there's your horizontal, vertical component of lift, and they make up this resultant force of lift in this direction, okay? So what we're saying is the lift splits into these two components. The angle here is 16 degrees. This is the opposite, this is the adjacent, this is the hypotenuse. So if we want to work out the vertical component of lift, it's the adjacent, so we're going to use cos of theta is equal to adjacent over hypotenuse, okay? So the vertical component of lift is cos of 16 equals the adjacent over 9.5. So this vertical component here is going to be 9.5 cos 16. Okay, and if you put that into your calculator, you're going to get 9.5 cos 16. And that gives you 9.1 kilonewtons. Okay. Now we want to then work out the horizontal component of lift. And the way that we do that one is, again, we can think of this as a triangle of forces. So this time that's the vertical component of lift there. We've just shifted it across here. Vertical component of lift, horizontal component of lift. And then the resultant of those two is that vector in that direction, the vector at the 74 degree to the horizontal angle. So this time, this is the adjacent and this is the opposite, and the 9.5 kilonewtons is the hypotenuse of this triangle. So again, we're going to use cos theta. So cos of 74 this time is equal to adjacent over 9.5. And that means that this horizontal component of lift now is going to be 9.5 cos 74. Okay, and when you do that, you get 9.5 cos 74, which gives you 2.6 kilonewtons. So that is 9.1 kilonewtons. This here, the horizontal component, is 2.6 kilonewtons. And by virtue of the fact that we're moving at a constant speed, there must be zero resultant force. Therefore, this drag force here must be 2.6 kilonewtons in the opposite direction to cancel out that one. And this weight must be 9.1 kilonewtons because it's opposite to this force and they cancel out. So there's your weight, there's your drag.